Hello everyone. In this video, I want to work through an example problem of just counting and how to place objects into boxes with a bunch of variations. And so the basic problem that I want to consider is how many ways are there to put 5 balls into 3 boxes? 5 balls in 3 boxes. But we also want to make sure that each box has at least 1 ball in it. At least 1 ball. And then we want to look at all the variations of this. For example, if the balls have labels on them or don't have labels on them, and or if the boxes have labels on them or don't have labels on them. And really the question that's getting at, are these things distinguishable or indistinguishable? And so there's a lot of examples of problems where either one of those are things that we need to worry about. So let's think about all the possibilities. So I want to think about all the possibilities. So there's 4. The balls can be distinguishable or indistinguishable, or the boxes can be indistinguishable or indistinguishable, and those are independent. So I've got 2 times 2, 4 possibilities. So let's do all 4. But let's start with the one that's probably most like what we've talked about in class already, which is the case. If you remember that when we looked at stars and bars diagrams, that actually winds up corresponding to a case where our objects are unlabeled, but the boxes are basically labeled. It matters sort of which things go where. So that case we can, I'll do that one first. And so in that case, we can think about it. The one wrinkle we have to take care of is, what do we do with this requirement that each box has at least 1 ball in it? And so if the balls aren't labeled, then there's really only one way to do that. That means we basically, again, if I use this sort of stars and bars kind of picture, I've got 3 boxes and each box has at least 1 ball. So I have to basically start out with that. And if I'm not labeling these balls at all, then they're all indistinguishable. There's only one way to draw this picture. But then all I have to figure out is, okay, I'm starting with that. Now the remaining problem is I've got 2 more balls to distribute. I had 5 balls in total, and it's really just a question of how do I arrange 2 balls into 3 boxes? And so it's really just a whole separate stars and bars problem with just 2 objects and 3 boxes. And so, again, I've got 2 stars to distribute and 2 sort of vertical lines separating the 3 boxes. And so if you remember the formula there, it's basically going to be 4, choose 2. There's basically 2 possibilities where I could put those symbols. But to just draw out what are the possibilities. Possibilities are, okay, I could have something like that. I could put just 2 in one box. And since the boxes are labeled, I could also put, that's different than putting them in the middle box, which is also different from putting them in the box to the right. But the other possibility is I put the 2 balls in different boxes. So I could do, for example, that. I could have them in the first 2 boxes, and again we can see there's basically 1 empty box, and so I have 3 choices of which box I want to be empty. I could have the box in the middle be empty, or I could have the box in the left be empty. And so all put together, there's 6 possibilities here. And so, but just to remember our formula, it was sort of, if I've got 2 balls and 3 boxes, and I take those 2 added together minus 1, choose the number of boxes, then that's 4 choose 2, which is equal to 4 factorial over 2 factorial 2 factorial, which is equal to 4 times 3 over 2, which is 6. Great, we got the same number. Okay. So that's probably the first one. One of the easier ones to think about is balls unlabeled, but boxes labeled. We've got 6 possibilities. Now that we've got that out of the way, we can actually go to the case where both the balls and the boxes are unlabeled and think about that, because if we don't have the boxes labeled, that means we don't really care. We consider the boxes indistinguishable. And so in fact, we can use what we've already drawn here to say, well, if the boxes are indistinguishable, then these cases where I have two balls in one box, they're all indistinguishable. So there's really just one possibility here. And again, here, I've got three boxes, two that have one ball each, one that's empty. Again, if I can't really distinguish the boxes, then these are all equivalent. And so I've got one possibility here. And so in that case, where both the balls and the boxes are indistinguishable, then I have only two ways to distribute 5 balls in 3 boxes. So we're already halfway done. So let's remember those numbers, hopefully. But now we have to think about, okay, we've done all the cases where the balls are indistinguishable. But what if we start labeling the balls? And there, what we could do is I could give them letters or numbers or whatever, but I'm basically asking, let's sort of start drawing this out and think about, we can use similar arguments to work it out. So for example, again, we have this requirement, that's a little bit of a sticking point, of we have to label, or sorry, we're required to put, we want each box to have at least one ball in it. So one way we can think about it is that we can take care of that first. We can say, okay, I've got 3 boxes. Now, the one thing we still don't care about is we don't really care about the order. Like if I'm going to call these balls A, B, C, D, and E, and I have balls A and B in the first box, I don't really care about, all I care about is that those balls are in that box. I don't care if it's A, B, or B, A. So I don't care about permutations there, so that's something to keep in mind. But that's something we can use to think about this. So for example, let's think of these 3 boxes. Maybe I'll just draw 3 boxes here. And I'm thinking of ways to distribute these 5 letters into these 3 boxes, and I need to have 1 letter in each box. So let's just think of how many different ways there are of doing this. So for example, we sort of saw already that if each object, or sorry, if each box has to have 1 object in it, then I have sort of 2 types of remaining possibilities. Either I've got 2 more in one of the boxes and 0 more in the other 2. So I've got basically 3, 1, 1 in terms of the number of objects in each box, or I've got 2, 2, 1. And there's different ways of arranging those, but that's one way we can think of arranging this. So let's try to see if we can figure out how to count this up. Now that we're actually labeling the boxes and the balls. Well, we're labeling the balls, and we're going to consider both possibilities for the boxes. So all right, let me do the 3, 1, 1 kind of arrangement first. So for example, let's look at this first box that has, just for the time being, let's say we've got 3 in this first box, 3 balls. So I've got 5 choices for which ball I put in there first, A, B, C, D, or E. I'm going to put 3 balls in here. So I've got 5 choices for the first, 4 choices for the second, and 3 choices for the third. But I said I don't care about the ordering here. I don't care, like if I choose A, B, C, that's the same as choosing C, A, B, or whatever. So this is actually, the formula I should use is the choose formula. It shouldn't be just 5 times 4 times 3. So I've got 5, choose 3 possibilities for the number of balls I've got in that box. And then, okay, next box. In this case, so I've put 3 balls in this box, and I've got this many ways of doing that. Now I have 2 balls left. So I really only got 2 choices here. And then once I make the choice of which ball to put in this box, the choice of which ball I put in, I've only got 1 ball left, so I don't have any choice as to what goes into that box. So I could say, okay, if I put 3 balls in the first box, 2 in the then I have only 2 choices left after that, and that sort of fixes everything. And so in this sort of 3-1-1 arrangement, how many possibilities are there? Well, 5 choose 3 is 5 factorial over 3 factorial 2 factorial, which is equal to 5 times 4 over 2. But I'm also multiplying it by 2 then here. So this will be, let's see, that's 10, and then I'm multiplying by 2, so that's 20. So I've got 20 ways of doing this sort of 3-1-1 arrangement. Let's leave that aside for the moment. And let me draw out, what about the other sort of type of arrangement, the 2-2-1? Maybe I'll draw boxes here. I didn't really do much with the boxes. But we can make a similar argument here. I can just go through my possibilities. I am going to choose 2 boxes, or 2 balls to go in the first box. Again, I don't really care about the difference between AB and BA, so it's 5 choose 2. Now I've got 3 possibilities left. 3 balls left to put in the remaining boxes, and I'm going to put 2 in this box and 1 in the last box. And so here I've got 3 balls left. I've got 2. I'm choosing 2, so I can do again. I don't care about order, so I've got 3 choose 2 ways of doing that. And then once I've chosen those balls, again, I'm left with just 1 ball to go in the last box, and I'm done. I don't have any choice there. And so if we count this up, then we'll have 5 choose 2, which is 5 factorial. It's the same thing as actually 5 choose 3. So that's 10. And then I have 3 choose 2. That is just 3. Sorry, I wrote it as a fraction. Well, no, I meant to do that. Yeah, that's just 3. So I've got 30 possibilities here, except I have to think about whether, now I got to think a little bit about, am I looking at distinguishable boxes or not? Because the answer to none of these is 50. So now I gotta think about, are these boxes, do I care about the boxes or not? So for example, if I care about which box they go in, so I had 20, here I said I had 3-1-1. So I have 20 ways of sort of doing 3-1-1. But that's distinct from having sort of 1-3-1, which is also distinct from having 1-1-3. And none of those are going to overlap. Those have completely different number of balls in each box. And if I consider the boxes indistinguishable, so that means there's basically 20 times 3 ways of doing things if the boxes also have labels. Because I could put 3 things in the first box, or 3 things in the middle box, or 3 things in the right box, but it's the same calculation each time. And I've got 20 ways of doing all this each time, so that's 20 times 3. If I look at this, here I've got 10 choices for the first box, 3 things of basically distributing, 3 ways of distributing basically everything else. And again, if the boxes are labeled, then we've got to think about sort of how many possibilities are there. But again, we've got 2 things in one box, 2 things in another box, and 1 thing in the remaining box. And so we've got, but we could also have 2 things, we could have, we've got 3 possibilities again, basically. Because we could have the box with 1 object be the final box, or the middle box, or the first box. And so, and just so there's also 30 times 3. Let's just check, make sure that we're not double counting something. Because you might say, well, what if I swapped, if the boxes are labeled, then what if I swapped things here to here? But we've already accounted for that because we've sort of said 5 choose 2 here, 3 choose 2 here. So if I pick, this already includes the possibility of saying, for example, AB here and then CD here versus CD here, AB here. That's all included in this calculation of 5 choose 2 times 3 choose 2, because I allowed myself to pick from any of the things there. So in the case of everything labeled, balls and boxes, then we have 20 times 3 is 60, 30 times 3 is 90. We have 150 total ways of distributing all those things. Now we have the somewhat subtler question, though, of the one we have left is if the balls are labeled but the boxes are not. And the reason this is subtler is we have to make sure we don't overcount. So let's go back to this picture, though, and say, okay, if the boxes are not labeled, so let me look at this top one first, the sort of the 3-1-1 arrangement. If the boxes aren't labeled, then I no longer care about the distinction between 3-1-1, 1-3-1, or 1-1-3. Those all look identical. But also, I need to be careful because if I've got only 1 thing in this box and 1 thing in this box, and the boxes aren't labeled, then I don't really care. Like if A were in this box and B were in this box, I don't really care about, that's, if the boxes aren't labeled, then that's indistinguishable from B being in this box and A being in that box. So that means if the boxes aren't labeled, then I don't have 20 possibilities. I don't know if you can see the red real well, I really only have the 10. Because once I choose which 3 to put in this box, that box is special. It's got 3 things in it. But then I don't really care about the difference between A, B in the other boxes or B, A in the other boxes. So in that case, I'm just going to write a 10 up there to indicate that really, if I've got that arrangement and the boxes are indistinguishable, then I've only got 10 ways of doing that. And here, we're going to have a similar issue. Here I've already sort of written it out. Like this counts all the possibilities where these are distinct possibilities. But if the boxes are unlabeled, then I do not care whether this one has AB and this one has CD, or this one has CD and this one has AB. So I've got to think about that and say, okay, it's not going to be 30. And in fact, what happens is here, and again, I don't care where the boxes are in terms of this picture. Like 2-2-1 is same as 2-1-2. Like I don't care about the ordering of the boxes. They're indistinguishable, so all I have to look at is the 2-2-1 picture. And here, since these 2 boxes have the same number of objects in them, I can swap them without changing anything if I don't have the boxes labeled. And so it basically boils down to how many ways are there of swapping 2 objects, or how many permutations are there of 2 objects, and there's just 2. And It's basically just saying I could swap the two objects and not change anything. So I have got the 10 times the 3, but I want to divide that by 2 to account for the fact that I don't actually care whether I've got like AB in one box and CD in the other. So here, I have actually 30 divided by 2. I just have 15 if the boxes are not labeled. And so then putting those two together, that means that the balls are labeled and the boxes are not labeled. Then I have a total of 25 ways of doing that. And that's probably the trickiest one to kind of work out in the C, because we're kind of putting together all these labels in the balls and have to do permutations or choose combinations of those. But thinking through how to deal with the indistinguishable boxes actually ends up being a little more work. But to just sum up, our final answer then is for all the combinations, and let me just clear this off and write it down. We said that if everything has labels, boxes and balls labeled, balls and boxes labeled. There's 150. If just the balls are labeled, there's 25 possibilities. If just the boxes are labeled, there's 6 possibilities. And then we said if there's nothing's labeled, there's only 2 possibilities. And that was 5 objects in 3 boxes with the restriction that each box have at least 1 object. All right, so that's an example of how we can use counting and how it's really important actually to keep track of whether we're sort of considering objects distinguishable or indistinguishable, because we can see that it changes the answer quite a lot in this case. It's a factor of 75 from the totally unlabeled case to the totally labeled case. And that has a lot of implications actually in a lot of applications. All right, thanks for listening.